Well, first, I'd like to say thank you for the invitation to share some of the details of this project topic, electro-optic polymer development and performance measurements for telecommunication and quantum applications. I also would like to thank UCF and the Office of Research and IMEC USA for making this project possible. Before I jump into the details of the project, I want to give you a broad sense of what my research group does. We look at the functional materials for sensing applications. And what this means is we're really focused on measuring the inter and intramolecular interactions of polymers with their environment. So the team that's in the trenches is here on the left. They're a great group of individuals, and I enjoy working with them. And I also have collaborations throughout UCF and beyond. But for this particular project, the collaborators here are Artyom Masanov, Fernando Uribe Romo, Enrique Del Barco, and Kyle Renshaw in Creole. So the project motivation stems from part of what Gufang was talking about before, is we need to be able to have faster, transmission, and we have so many more, let's say, devices, for example, connected to things like the internet, as in the IoT. We are having an estimated 85% increase in IoT connections between 2020 and 2025. This translates to at least 24 billion different connections. And it's not just about the IoT, it's about online data and media that's being streamed and stored. And the thing is that we don't have the current technology to meet the increasing demand for where we need to be. And so in that way, we need to develop advanced optical modulating materials. And this is where second order nonlinear optics comes into play, and specifically the electro-optic effect. And there are other second order nonlinear optic effects as well that are listed here, but I'm really focused on the ones that the electro-optic effect, so that we can use it in that Mach-Zehnder modulator that Gufang so nicely described in his previous slide. And it's through having this nonlinear optic material in one of the arms, wherein you have an input light source, let's say a laser, that is going through a waveguide and then splits into two arms. One is the reference arm, and the other one has the nonlinear optic material present. And when you apply an external electric field, you can change the phase of the photons that are passing through the NLO material. And when they rejoin together at the end, you either have a signal that's in phase, so you have a signal, or the photons are out of phase, so you have no signal. And there are different types of nonlinear optic materials, as Hassan will talk about some inorganic ones likely in his talk next. But for me, I'm focused on the nonlinear optic material of electro-optic polymers, or EOPs. EOPs are a great type of material to be using for nonlinear optic applications because they are already compatible with foundries for semiconductor processing. They can exhibit very large electro-optic coefficients. They are easy to use, low cost, and they also have low power consumption. Electro-optic polymers work by using an asymmetric chromophore that's input into a polymer host, forming a composite. And the asymmetric chromophores generally have an electron donor and an electron acceptor that's connected through an electron bridge. Now, when you first form this composite between the chromophore and the polymer, you have an electro-optically inactive material. The thing that we need to achieve is a lack of inversion symmetry. So in order to form a non-centrosymmetric material or matrix, we can achieve this by doing something called thermally assisted electric pulling. And in thermally assisted electric pulling, if you increase the temperature above the TG or the glass transition temperature of the polymer composite while applying a large electric field, you can force the chromophores to rotate about their z-axis so their dipoles align in the direction of the electric field. Then if you cool this back down with the voltage applied, you can so-called freeze the chromophores in a head-to-head acentric order state, and thus giving an electro-optically active material. The thing is, though, I drew all of these in a head-to-head acentric order vertically, but the fact of the matter is, because you have a plus electron donor and electron acceptor on one molecule, an adjacent molecular chromophore will tend to aggregate very strongly in a head-to-tail fashion. So what really happens with the electro-optic polymers is you tend to get a strong aggregation, and the higher the hyperpolarizability, which is a predictor of the nonlinear optic effect, then the more propensity you have for aggregation. And when you do have the electro-optic effect, sometimes there's low spatiotemporal stability due to relaxation of the chromophores to an isotropic state. So one of the things that I want to look at specifically in part of this project is how does the polymer chemical, structural, and physical properties influence the electro-optic effect. So a lot of work has been done in looking at the chromophores, but there's a lot that we don't know actually about the polymer. So let's say if we're looking at the electro-optic effect and we want to measure the R33 effect, or the electro-optic coefficient, and measure its stability over time in the presence of an electric field, then in terms of the polymer physical properties, we can look at something called tacticity or stereoregularity. This is the direction of the bonds on the backbone of the polymer chain. This is an important component to study because we know in the polymer field that if you have a difference in tacticity, you can have a difference in how the polymer itself ages, which can affect the spatiotemporal stability. And also, when you have different tacticity, it can also affect the free volume pore size, which is an important component because the free volume space between the polymer chains is where the chromophores reside. And so for that reason, it's also important to consider the size and the shape of the chromophore and how those fit within the free volume spaces of the polymers that we're making. Another thing that's important to consider is the molecular weight of the polymer. We know in the polymer field that if you have a low molecular weight polymer, you have a larger free volume pore size, which could potentially allow you to have a larger chromophore loading. But we also know with low molecular weight polymers that you have more wriggling or movement of the polymer chains on the molecular level, which could potentially limit the spatiotemporal stability. So we want to find the optimal region that will help the angular rotation of chromophores to be optimized and remain there for the longest period of time. So in that case, one of the other things that we need to consider is to look at how the compatibility between the chromophore and the polymer exists. In general, polymers are hydrophobic and chromophores by design are hydrophilic. And so that's another reason why they tend to have strong aggregation. So if we can functionalize the polymer material to have a more similar matching between the polarities, then we could potentially improve the compatibility between the chromophore and the polymer by studying that at the interface. The next thing we wanted to do, now that we know which direction we're going in with the polymer, is to identify the chromophore. And we decided to make our own chromophore by using a computational structure feedback loop. And we did this in collaboration with Artyom Masonov, who has done the molecular simulation. So we drew a bunch of different chromophores that are asymmetric, and we went through and figured out theoretically what are the beta values and the dielectric constants from a theoretical standpoint. And we went through this feedback loop several times until we decided we had some molecules that gave us theoretical hyperpolarizability values that were sufficient enough to begin synthesizing chromophore materials. So the plot on the right is a result from this computation feedback loop. And what I want to point out on this graph is that this FTC class and the YLD class are the gold standards, or one of the gold standards of chromophores that are used in electro-optic polymers. And we wanted to identify a chromophore that has higher hyperpolarizability than that, but also high modularity in terms of how we can functionalize it. And so the blue ones are the ones we synthesize first, because each generation we got a little bit better and a little bit better. So right here are the ones that we have first synthesized. And I like two things about this particular chromophore class. One, if you notice all the R groups, these are sites where you can functionalize the asymmetric chromophore to modulate the size and the shape of the chromophore when you're looking at the compatibility between the chromophore and the polymer. The other thing I like about this chromophore is that it has very strong solvatochromism effects. And the solvatochromism is, in this case, having a blue shift, which means that as you increase the polarity of the solvents, so this is all from the same chromophore, and if you put it in like chlorobenzene versus THF versus chloroform and something more polar like acetonitrile, then this blue shift basically indicates that we have a stabilization of the ground level energy state of that chromophore. What this means is that the solvent molecules are able to stabilize the chromophore in such a way that it have a higher band gap in that case. This is interesting for two reasons, at least. Well, one, perhaps as a completely separate project, you might look at something like volatile organic compound selective detection colorimetrically as a different project, but focusing on the electro-optic polymers It's also interesting to say two things. One is that the chromophore itself has, because you see the difference in the solvatochromosm and it's very strong, that tells us that the polymer likely does have a very large hyperpolarizability. And so that's a plus, positive. But the other thing is, because there is such a strong shift in the small change of solvents, that also means that it's especially important to identify polymer materials that have higher compatibility with the chromophores in the first place. So now that we have the groundwork laid for that, we want to figure out how to get the electro-optically active films in the first place. So here we built ourselves in the lab a thermally assisted electric pulling setup so that we can actually achieve some electro-optic activity. And then through a collaboration with Kyle Renshaw and Creel, and many thanks to him and his students for helping to set up an electro-optic coefficient measurement method called the Tangman method. What I'd like to do as part of this project is to actually integrate our polling capability with the measurement of the electro-optic effect. And if we can do this, then we can begin to measure how the R33 value or the electro-optic activity is changing while we're actually polling the sample in the first place. This gives us an idea about how to measure the angular rotation of the chromophores about their z-axis when the dipoles align in the direction of the electric field. And the other thing we want to do as part of this project is through an exciting collaboration that's new with Enrique in physics, who has graciously allowed us to use his cryostat, is to build a sort of modular setup around the cryostat so that we can measure the electro-optic activity at ultra low temperatures, so that we can begin to look at not just telecommunication applications, but also quantum applications as well. So in summary, we need advanced optical modulating materials. And we can look at this in terms of the electro-optic effect, perhaps through electro-optic polymers, if we can better study the chemical and physical and mechanical or materials properties of polymers and how they interface with the chromophores at a molecular level. So again, I'd like to acknowledge the UCF Office of Research and IMEC USA for making this project possible.